Hi guys, today in this video we will design a common emitter configuration, specifically NPN transistor. As you can see, I draw it in this way. This is the emitter configuration that we're going to design in this video. Before we begin, I'd like to read this quote. So the greatest energy of success is ease. Okay. So um, so let's begin with designing the common emitter configuration. Um, as you can notice, the RC, RE1, and RE2 are colored in pink, and R1 and R2 are separated in color. It's because we're going to start in this one and then followed RC, RE1, RE2, followed by R1 and R2. Okay, so the first thing that we begin, so this is the requirements. So the requirements is we should have a voltage gain of 5. Okay, so to begin, so um we'll be going to finalize or prepare the formula for voltage gain. Okay, voltage gain is approximately defined by the ratio of resistor in collector and then RE1. And since we know that because we have a negative sign because it produces an inverting output. Okay, so but it's useless if we're going to get the of negative value of the resistance, because there's no such thing as negative resistance. Okay, we're going to rewrite this as RC over RE1, because that's what we're going to use. Okay, so for practical purposes, we're going to make the voltage gain in this equation, or in this process, added by 2. So our new voltage gain now would be 7. It's because if we set the voltage gain by 5, um, um, in real life scenario, considering all of the aspects, it will decrease. So that's why um, I've set a higher gain in this one for practical purposes, and also to achieve our goal. Okay, so therefore, manipulating this equation would result into 7 RE1 is equals to RC. Okay, so that's our um, first equation. Okay, so the second equation would be the Q point. Q point. Okay, so operating point. It's important because wrong placing of Q point would result into the distortion of the signal. So think of it this way. Okay. Mhm. So we're going to have um, a quick review of DC load line analysis. Okay, and this would be our um, VCE, and this would be our IC. Okay, so as you can see at this point, this is the VCC. Okay, okay, so the best point for the operating Q point would be this one. Mhm. So that would be VCC divided by 2. So that would be the most practical um, point that we have, because the very reason for that would be this one. If, for example, we have um okay, so we have like this. Okay, so as you can see, this one is trimmed down and this one too. Another example is like this. Let's change it the color into more visible. Okay, so there is a signal like this, so the signal would be okay. So as you can see, this one would be trimmed, so you will have a signal of like that, because there are no um battery or energy to amplify that signal. Okay, so that's why um, for practical purposes, the VCE should mhm, should have a value of VCC over 2. Okay, so with that being said, let's begin finding the Q point. Okay, so by doing this, VCC divided by 2, and our VCC is 12, therefore 12, therefore 6. So that would be our VCE. So that would be the expected output between the collector and then the emitter. Okay, so the next one would be to find the operating current, collector current. Okay, so the formula for that, or to derive that, would be this is pretty important. So this one. Okay, so I'm just going to draw. Okay, so as you can see, this is our configuration. So by doing a loop, all right, so by doing the loop, starting from here, our VCC. Okay, so starting from there, um IC from the voltage drop here, the collector, then the 6. So this is our VCE. So the number 6 would be the VCE. So that one. VCE. Okay, so that's the VCE, and then the voltage drop, and or also known as the VE. So this one. So this is the VC. Okay, so um by using common sense, you will notice that this one should have a voltage drop of 3 volts, and this one should have a voltage drop of 3 volts, and then this one is 6 volts. So that's why it's expected that in this one we will set this as has a voltage drop of 3 volts, and then this one also a voltage drop of 3 volts for symmetry purposes, and also for um, so that it would be much easier to solve. Okay, so if you do the math and then manipulate it, but before that, I'm going to establish that IC is approximately equal to IE. The very reason for that is because if we try to do it accurately, it would be hard and also difficult. So for practical purposes, we also assume this one. Okay, it's because the value of current in base is small. So in this case, we could just ignore it for practical and simplicity purposes. Okay, so now evaluating this one. Okay, so remember that you have a value of 12 here. So as you can see, this one would be 6, and then, okay, so just to write it down, so I'm going to simplify this. So this one would be 6 is equals to, oops, this one is not included, okay? So the VC, 6 minus, okay, so 6 minus IC RC minus IC, again our assumption, RE1 plus RE2, okay, equals 0. And doing the math would be, just transpose this first. So 6 is equals to IC RC plus RE1 plus RE2. So that's why we have this. IC is equals to 6 over RC plus RE1 plus RE2. But remember that we have this kind of expression here, okay, from our equation 1. So therefore, 6 would now be, RC is 7 RE, right? 7 RE1 plus RE1 plus RE2. It would now be 6, 8 RE1 plus RE2. Okay, so we have now another equation. Okay, so we're going to use this. So just take note of this. So this is the ICQ, or our operating current. All right. So that's our second equation. Now we're going to the next equation. Okay, we're going to use that in a minute. Remember that the VE, or if you take your multimeter here and then multimeter, then connected it to the ground. So this one is expected to have 3 volts. Therefore, it should have 3 volts. Therefore, and then the relationship of that would be IC RE1 plus RE2. Correct? Correct. Okay, so now simplifying this would now be substituting the value of IC into this one. Okay, we would now have a 6 over 8 RE1 plus RE2. This one would be RE1 plus RE2. Okay, so now we have this one. Okay, and so now we are going to find the RE1. Okay, so a rule of thumb here, we're going to assume the value of RE2. So the best tip here is that we should use a value of resistor that we have and also easy to obtain. So in my case, I'm going to use 510 ohms. Okay, so doing that and doing the algebra, you will find that the RE1 would now be equal to, drumroll please, 85 ohms. Okay, so I will leave it to you on how you will plug in those value RE2 510 and then do some manipulation, and then you will arrive at that point. Okay, so now remember that we have from previous equation, so this one Okay, okay. So remember that. So 7 RE1 is equals to RC. Plugging the RE1 here would result into the RC equals to 595. Okay, ohms. Okay, so we're going to highlight the value here, highlight here, and then this one. Okay, so now we finished this one. Now we're going to find the biasing. Okay, okay. So to begin with that, we're going just but before that, we're going find first the ICQ, or the operating current, because it's important for the biasing purposes. Okay, so now we're going to find the ICQ. Okay, so ICQ is just an easy one, because you'll just have to use this formula 6 8 RE1 plus RE2. Now, you could pause the video and then plug it in your calculator. So, um, and that you will result into 5.042 milliampere. Okay, so that's the finding the ICQ. Alright, so now what we're going to do here next is we're going to find the value of RTH. RTH. Okay, so the formula for that would be 10 RTH is equals to 1 plus beta over I multiplied by RE1 plus RE2. Okay, so using that formula, so it would be 151, because we have 150 beta, so it would now be 85 plus 510 ohms. Okay, so and finding the value of RTH would now be equal to 8984.5 ohms. Okay, so RTH is the combination of R1 and R2, R1 and R2 in parallel. Okay, okay. So we're nearly done. We're just going to find the VTH. Okay. Mhm. After finding the VTH, it's just super easy to find the R1 and then the R2. Okay. So in this case, so the formula for VTH would be VTH is equals to VE, and you know that this is 3, plus VBE. So in this case, I'm going to make it 0.7. So plus ICQ, and then beta, and then the RTH. It's 0.7 because this diode part. But if you wanted to be much more specific, you could look into your data sheet. Okay, so plugging in the formula would be 3 plus 0.7 plus the ICQ is 5.042 milliampere, and the beta is 150, and then the RTH would be 8984.5 ohms. Okay, and that would result into approximately 4 volts. Okay, So I just round it off. Okay, so now for the last step. Okay, so for the last step would be to find R1 and then R2. We deserve a drum roll here. Okay, so mhm, mm, R1 and R2. Okay, so to find R1, the formula for that would be R1 is equals to RTH, mhm, and then VCC, and then VTH. That's why we find those value. R2 is equals to RTH, same numerator, it's just that the denominator is different. VCC minus VTH. Okay, so that's pretty easy because we all have this value. All we have to do is plug it in. So I'm going to plug in the um, to find the value of R1. So 8968984.5 and then 12 and then the VTH would be 4. And then the result would be 26953.5 ohms. Okay, so you'll just do the same thing here. It's just that you will add VCC and then if you plug it in calculator, so I leave the rest up to you. It would be 13476.8 ohms. I rounded it off. Okay, so that's our resistor that we're going to use, and it has a characteristics of approximately 5, a factor of 12, and it has you know, a pretty good um, operating point. Now, up to this point, you're ready to go, and you could do your prototyping. But if you wanted to do some simulation, you could watch a few more minutes with me. So to do some simulation, all right. So as you can see, I've plotted it. So so the output would be in the channel B, which has a blue one, and then the input would be in the red one. So as you can see, this is the R1, R2, the collector resistance. So RE1 and then RE2. So the value of capacitor is just for simplicity and also simulation purposes. Okay, so it's not much critical here, unless you wanted to be be aware of the frequency response. Okay, so I've modified this one. It has you know, an HFE of 150, just like what we solved. Okay, so we're going to use zero point 0.2 voltage peak, and then the frequency would be 1 hertz. Okay. Okay, so as you can see, this is the configuration. Okay, so we're going now to run. Okay, so first, as you notice, we have an almost half of the VCC, but due to the um, simplicity and also the assumption we've made, it's not accurate up to this one. But as you can see, it's near to the half. Okay, and also let's look at the graph. Okay, so in this one, as you can see, um, it is amplified. So if you wanted to check, here is the output and here is the input. So as you can see, if you do the math, It's around 4 point something. Okay, so that's it for today. So as you can see, um, you could just adjust the value here to have it at the exact 6 if you wanted, and also you could also to check the tolerance and also um, value if you wanted to execute it in the real life. So this formula that we've used is tested. I've tested it, and also it's a good thing that we have this kind of formula that we're going to use. So in this video, you've learned a lot in designing a common emitter configuration, specifically NPN transistor. So I'm Jerome, and thank you for listening. Goodbye.